In this lecture, we're going to learn about various free energies. Now, of course, free has got nothing to do with dollars or rupees. It will have something to do in terms of the amount of work that one can extract from a system. The concept of free energies goes back to Helmholtz and to Gibbs. We'll study them shortly, but they are important because these principles derive from the second law of thermodynamics, which says that the entropy of the entire universe has to keep increasing. It can never decrease. From this, a minimum principle is derived, and minimum principles have a long history in physics. So, for example, you may have heard of the Fermat principle, which says that light takes the shortest part to go from point A to point B. But there are other minimum principles, like that of the principle of least action, from which we derive all of quantum field theory, string theory, everything. Free energy is a basic concept in thermodynamics. The first kind of free energy important in thermodynamics is associated with the name of Hermann von Helmholtz. This is most useful when you have a system that is allowed to exchange heat with the outside world. So here the reservoir provides constant temperature. However, this system S cannot change its volume. That is to say, its shape cannot change. This means that it cannot do any work, because work is P times dV, pressure times the change in volume. And so if the volume is constant, then no mechanical work can be done. So now let's look at the second law of thermodynamics, which says that the entropy of the universe always has to increase when the universe is away from equilibrium. Now, the entropy of the universe has got two parts. There's the entropy of the system, and there's the entropy of the reservoir. So the sum of the two has to be positive. Well, let's look at the entropy of the reservoir. This reservoir has given an amount of heat dq to the system, that is to say it's lost dq, and so the change in entropy of the reservoir will be minus dq divided by T. However, the heat that has been given to the system here has resulted in an increase in the internal energy of the system S. dq is equal to du, and that's just conservation of energy, and that's because this system could not do any mechanical work. So, this then tells us from here that ds minus du divided by T is positive, which means that if I multiply this equation by T and I take ds to the other side and this to the other side, that d of this entire quantity has to be negative. Now remember that T is constant, and so dt is equal to 0. Let us now define the Helmholtz free energy. A is the Helmholtz free energy. It's equal to the internal energy U minus the temperature of the reservoir into the entropy of the system. So obviously dA is equal to du minus Tds. As I said, there is no need to differentiate this T because dt is equal to 0. So then this condition over here becomes dA is negative when the system is away from equilibrium, and when the system is in equilibrium, then dA is equal to 0. Well, of course you know this, but let me remind you that dA is the change in the value of A. So it's the final value of A minus the initial value of A. Let's make a little picture of this. So imagine that the Helmholtz free energy A is plotted against some parameter. This parameter here could be time, or it could be pressure, or something else. The point at which A is lowest is where the equilibrium state will be. That's because if we go a little bit to the right or we go a little bit to the left, then dA does not change at equilibrium. However, if you are elsewhere, like say over here, then if you go a little bit to the right, then you go up. If you go a little bit to the left, then you go down. So suppose the initial state was this, and that initial state was not in equilibrium. Well then, it will try to minimize the value of A, and so it will make the transition from here to here. The second law of thermodynamics does not tell you how long it will take to go from here to here. It just tells you that this is the stable state, the equilibrium state, and that if there is any other state, it will move towards that state. But it does not provide you the time. That is a job for non-equilibrium thermodynamics, which we will not consider in this course. Now here is an example of how a system goes from an initial state to a final state, that final state being the equilibrium state. So imagine that we have some gas which is confined to this part of the box, and in between we have a wall. That wall is suddenly removed, and so this gas then expands outwards. That's what we expect physically. How do we see this in terms of the Helmholtz free energy? Well, there is no change in internal energy of the gas. You remember that if it is an ideal gas, and that's what we are considering here, then the internal energy only depends upon the temperature T. So if the initial temperature and the final temperature are the same, that means that there has been no change in the internal energy of that ideal gas. So then why? What principle made this gas expand outwards like this? Physically we can understand it, but now mathematically we are able to understand it as well. Because if you look at the difference in the Helmholtz free energy of the final state and the initial state, well, they are different. So, although there was no change in the internal energy of this system and that system, however, the entropy of this system is less. You can see intuitively that there is less disorder over here and more disorder over here. So the final entropy minus the initial entropy, we call that delta S, is then a positive number. And so delta A, which is the final A minus the initial A, becomes minus T delta S. And delta S is positive, as I said. There's more entropy here, less entropy here. So the final entropy minus the initial entropy is a positive number. And so therefore, delta A is a negative quantity. Therefore, this happens spontaneously. You didn't have to push this system from here to here by providing it any heat or temperature or pressure. It happened by itself. Now you see, this is very different from what happens in normal classical mechanics. There, a system will try to minimize its potential energy. Here, in this thermodynamic system, the system will try to minimize its Helmholtz free energy. So the system has gone from here to here. It's not done any work. In fact, you could say the amount of wasted work is this much over here, T delta S. If we had a piston over here that was pressured by the gas to move away, we could have extracted work from it. In fact, we saw this in an earlier lecture. Let's move on to the Gibbs free energy. This is going to be different. Here we will insist that the system provide not only a constant temperature, but also a constant pressure. In that case, to reach equilibrium, a system will move so as to minimize what we're going to define as the Gibbs free energy. And the Gibbs free energy is a very, very useful quantity, especially for people doing chemistry or looking at the early universe or for so many other applications. G, if you know how to calculate it, will allow you to find the maximum available energy that you can extract from such systems. In the Gibbs free energy, as I said, the reservoir will provide you a constant temperature, a constant pressure, P, and now the volume is allowed to change, which means that this system can do work. Let's call that small amount of work dW. This you already know, that the change in the internal energy of the system S is equal to the amount of heat that it receives from outside minus the amount of work that this system performs. Of course, dW is just PdV, the pressure into the change of the volume. We've already encountered the enthalpy. The enthalpy is the internal energy U plus the pressure times the volume. That's the definition of enthalpy. And that means if I make a small change in U and a small change in V, but keep P constant, then the change in enthalpy will be equal to du plus PdV. Let's see how the entropy of the reservoir changes, and that's equal to the heat that is lost by the reservoir divided by the temperature of the reservoir, and exactly the same as earlier. However, now dq, as you can see from here, is equal to du plus dw, which is obviously this quantity here, minus du plus pdv divided by t. And that from above is equal to minus dh divided by t. And so we can write the second law of thermodynamics as ds minus dh divided by t has to be positive. It has to be positive away from equilibrium, and at equilibrium, of course, this is equal to 0. Now, let me multiply this by t and then take these terms, both of these terms, over onto the other side. So, if I define now the Gibbs free energy as H minus Ts, remember that this is different from the Helmholtz free energy, where you had A was equal to U minus Ts. Now it's G which is being defined in this way. Well, then dG is equal to dH minus Tds. So the second law of thermodynamics, which says that the entropy of the entire universe can only increase, that becomes ds minus this. Now you see over here that the ds cancels out, and so we are left with the condition that away from equilibrium, dg is negative. This is exactly the same as for the Helmholtz free energy, where we had dA was negative away from equilibrium. And again, we conclude that dj is negative and dj is 0 at equilibrium. I'm just repeating here what I did with A. Remember that dg is just the final g minus the initial g. At equilibrium, g is minimum. Away from equilibrium, then you could have an initial state there, and that initial state would then work its way down to the equilibrium state. So every state that is away from equilibrium will attain equilibrium. It doesn't matter which side you approach it from. It could be this side or that side. The really important point to grasp here is that every system which has constant temperature and pressure provided to it by the environment will seek to reduce its Gibbs free energy. So if initially it was here, it's going to come down to the equilibrium state. There are countless examples of applications, but let's look at chemical reactions. Look at this reaction, for example. Nitrogen naturally comes as a diatomic molecule, so nitrogen gas and hydrogen, which also comes as a diatomic molecule, can combine in this way. So one molecule of nitrogen and 3 molecules of hydrogen can make 2 molecules of ammonia. Or we could have it the other way. 2 molecules of ammonia could dissociate into 1 molecule of nitrogen and 3 molecules of hydrogen. Now, the question is energy released in this reaction or in this reaction? Or instead, is it absorbed? We can ask, which of these reactions happens spontaneously, by itself? And we can ask, are the answers to these 2 questions temperature dependent? For this, we need chemical data. So look at this data for hydrogen, nitrogen, and ammonia. We need to know the enthalpy per mole, which is of course measured in kilojoules per mole, for all 3 substances. For hydrogen and nitrogen, that enthalpy is 0. Why is this 0? Well, that's because hydrogen and nitrogen naturally occur as diatomic molecules. However, we didn't have to put this at 0. This was for convenience. We could have taken a different starting point for the enthalpy, because enthalpy, that is the amount of energy you need to create these substances, is an energy, and to an energy you can always add a constant. Of course, you must add the same constant to all, but that constant makes no difference. So if instead of 0 over here, let's say we had some other constant, that would make no difference to the final answer. The enthalpy of formation of ammonia, however, is negative, and it's 46.2. Of course, we want to calculate the change in the Gibbs free energy, so let's look at the initial enthalpy first. That enthalpy, so looking at this reaction over here, we had 0 for this and 3 times 0 for this, and so the initial enthalpy is, of course, 0. Look at the final enthalpy. We have 2 moles of ammonia, so 2 of that times this minus 46.2, that's equal to so many kilojoules. The difference in the enthalpies, delta H, is negative, and it's large. It's minus 92.4 kilojoules. This is a reaction that releases heat, what is called an exothermic reaction. I remind you that delta H is the change in U, that is to say the internal energy, plus the work done on the environment, which is P delta V. But even for this exothermic reaction, we are not sure as yet. In fact, we cannot be sure as yet that it'll happen spontaneously. For this, we have to see how the Gibbs free energy has changed. So for that, we will need the entropy. That entropy per mole for different gases is given here for hydrogen, nitrogen, ammonia. These are quantities that are experimentally measured. I've just taken them from a table. However, these systems are simple enough so that one can use quantum mechanics to calculate these values. It's not easy, but it can be done. However, we will just take these as they are given to us from the table. So now let's look at the initial and the final entropies at standard pressure and temperature. Remember that all these enthalpies and all these entropies are defined at some value of the temperature and the pressure The standard pressure temperature means that the pressure is 1 bar and the temperature is 0 degrees centigrade. The initial entropy at STP is, let's calculate that, it's 0.192 plus the entropy of 3 moles of hydrogen gas, and the hydrogen has entropy per mole of 0.131, so we multiply by 3. Just add them up. That's 0.585 joules per degree Kelvin. Remember that entropy is always energy divided by temperature, and so it's joules per degree Kelvin. Next, let's look at the final entropy, also at the same temperature and pressure. So here we have 2 moles, and then we multiply by the value over here, and that gives us the final entropy, which is 0.386. The change in entropy at STP turns out to be negative. This actually makes sense. There's more disorder here. There was 1 mole of nitrogen here, 3 moles of hydrogen here, and they were moving around. There's a lot more disorder here as compared to the disorder of the ammonia gas, of which there are only 2 moles. And so it makes sense that delta S turns out to be negative, and that's the value here. Okay, now remember that the Gibbs free energy is the enthalpy minus Ts, which means that the change in entropy, remember the temperature is constant, so the change in the Gibbs free energy is equal to the change in the enthalpy minus T times the change in the entropy. Okay, so we do a little calculation of that. So delta G is equal to delta H, but delta H was 92.4 from here, minus the temperature. And remember that this is standard temperature, which is 0 degrees centigrade, 273 degree Kelvin. We multiply by the change in S, delta S, and now this is negative. So the Gibbs free energy here is greater than the Gibbs free energy here, which means that this reaction is spontaneous. It also means that this will not happen by itself. Now note one interesting thing here. This is negative, but this minus T delta S term turns out to be positive because there's a minus here and a minus here. Of course, this is the bigger of the 2 terms, and so we end up with a negative sign over here. And so we have indeed concluded that the first reaction will happen by itself at 0 degrees centigrade, but what will happen if we increase the temperature to 300 degrees centigrade? Will it still be spontaneous or not? And now let's do the calculation all over again. So here is delta H again, but instead of 273, I'm going to add on 300 over here, which means that the temperature factor is now going to be more important here than over here. And indeed, if you take your calculator, you'll see that this minus 92 is defeated by this term over here, and we end up with something which is positive. From this, we conclude that this reaction will not be spontaneous at 300 degrees centigrade. Or let's put it another way, at 300 degrees centigrade, this reaction will happen spontaneously. And we can understand that because at very high temperatures, these molecules will be colliding with each other, and when they collide, then the constituents will start to break apart. And so we will have a dissociation of the ammonia into nitrogen and hydrogen. If you heat this still further, then of course you would get atomic nitrogen and atomic hydrogen. Now, one thing that one needs to be a little cautious about, is this calculation over here accurate? Well, this one was, but I was using the enthalpy per mole and the entropy per mole at STP. And strictly speaking, I should not be doing that. I should be using the values which are correct, not at T equal to 0 degrees, but also at 300 degrees. So this is not a perfect calculation over here, but it is showing you one thing, that this temperature T is going to become more and more important as this gets large, as T gets larger and larger, to the point that delta G will eventually be dominated by this thing over here. So, although I cannot guarantee that delta G will be 21.6 kilojoules, it is obviously true that at high enough temperatures, delta G will become positive and dissociation of this kind will start to happen. The Gibbs free energy helps us understand a very wide range of heat-related phenomena, such as melting. We're very familiar with the melting of ice cream, of candles, of even iron, which melts when it is heated far enough. In all these cases, you have some solid which then turns into a liquid. If one looks at it on a diagram, as time goes on, the solid warms up until it reaches the melting temperature, and then it suddenly changes from being a solid to a liquid. The solid and liquid are both present together at this temperature, which is called the melting or the freezing point. Let the melting temperature be denoted by Tm, and let Hm be the enthalpy of melting. Now, enthalpy is relevant because all these phenomena that you see over here are happening under the pressure of the atmosphere, which is assumed to remain constant. As the solid melts, its entropy increases. This is quite obvious even in a physical way, because in a solid the entropy is low, there is more order, but as it melts, its constituents spread out and there is more disorder. We're going to denote the entropy of melting by Sm. Now, exactly at equilibrium, the ice and the water, the ice cream and the ice cream melt, or the wax, which is solid here and liquid as the candle melts on, they are in equilibrium. And the Gibbs free energy is at a minimum. So delta G is 0 as discussed earlier. Now, since G is equal to H minus ST, that means that from here we have delta H minus T delta S, which has to be equal to 0, from which the change of entropy is equal to the change in enthalpy divided by the temperature, and the temperature is the melting point. Now, it's reasonable to assume that the change in the enthalpy, delta Hm, and the change in the entropy, delta Sm, are reasonably constant. So let's ask, what would be the Gibbs free energy as a function of temperature? Well, delta G is delta H minus T delta S. And although delta H is a function of temperature, yet close to T equals Tm, this is a constant. Similarly, this delta S has been assumed to be a constant. And so the only dependence of the Gibbs free energy change on temperature comes from here, which we can now rewrite in the following way. Just take delta Hm out, in which case we'll get delta Hm into 1 minus T over Tm. And if you take Tm out over here, then we have achieved this. Now we know how the Gibbs free energy changes as a function of temperature. So if we look over here, if T is greater than Tm, then this factor here will be negative, and so delta G will be negative also. And that makes a lot of sense. Actually, if we plot it, it becomes even easier to see. So if we are above the melting point, delta G, that is to say G final minus G initial, is negative, which means that the ice will spontaneously melt. So to summarize, melting happens spontaneously if the temperature exceeds the melting temperature. If we apply this to water, then delta S here is 22 joules per Kelvin per mole of water, and so delta G of T will then be what you see over here. This is how the Gibbs free energy for water changes as a function of temperature. In all the examples considered so far, we did not allow particles to enter or leave the system. In other words, we considered a closed system. However, now let's look at an open system in which it is possible to exchange particles with the environment. In that case, we will need to make a slight change in our definition of G. G, as is defined here, is H minus Ts. H is U plus PV, so that's what it is here. And so dG is equal to this. It's du from here, pdv, vdp, and then each one of these can be changed, so tds and sdt. Now let's use the first law for an open system, in which case du is TdS minus PdV as we had before, but now we will allow the number of particles to be changed, or the number of moles to be changed. And so if you add more particles, then the increase in the internal energy is proportional to dN, keeping all this stuff over here constant, multiplied by this factor up front, which we will call the chemical potential. From here, mu can be defined mathematically as follows. Keep S fixed, which means put ds equal to 0. Keep the volume fixed, which means put dV equal to 0, in which case mu is du by dN, keeping S and V fixed. So this is the definition of the chemical potential. It measures how the internal energy of the system changes when you change the number of particles. Let's now put this into the above. So I'm just going to substitute du as it is over here, that's here, and then add on all the rest. So there's pdv plus vdp minus tds minus sdt. You put all that over here, and now you see that the pdv terms cancel, and you see that the tds here cancels with the tds here, and so we get simply vdp minus sdt and this term which is related to the change in the number. So that's plus mu dn. If you look at this, dg equals vdp minus sdt plus mu dn, it becomes clear that g depends upon p, t, and n. And so you can write g as a function of these three variables, p, t, and n. Obviously, the coefficients in front of each of these variables, p, t, and n, they are the partial derivatives of g with respect to that variable. In other words, if you look over here, suppose t is held constant, so dt is 0, and n is held constant, so dn is 0. In that case, v is equal to dg by dp at constant t and n. You can also see that the coefficient over here of dt, which is minus s, that's equal to dg by dt, holding p and n constant. And finally, you can see that the chemical potential, is dG by dN at constant P and T. So you can ask, why do I have two different expressions for mu? Here's one expression that comes from here, and here is the earlier expression. Of course, both are right, both are correct. However, here, this is not so useful because you have to differentiate the internal energy as a function of n, which is okay, but you need to hold the entropy constant. And experimentally, it's very, very difficult to hold the entropy constant. It's much easier to hold the pressure constant and the temperature constant. So this expression and this expression are both right, but this one is more convenient than the one above. Now, so far I've considered just one kind of particle, but what if there are many different kinds of particles, A, B, C, D, etc.? Then, of course, this can be trivially generalized. So this mu dn is actually a sum of all these mu dn's, mu A dna plus mu B dnb, etc., etc. We have to be careful, however, as to what is being held constant now. So, in defining mu A from this equation, not only must we hold P and T constant, we must hold the number of atoms or the number of particles of type B and C and D also constant. So therefore, there is a change in definition. Mu A, the chemical potential of substance A, is the partial derivative of the Gibbs free energy with respect to the number of particles of type A, holding the pressure, the temperature, and all the other particle numbers equal to a constant. Now, all this is fine as a matter of mathematical definition. However, how does one understand this chemical potential defined in this way physically? Why is it that the presence of atom B or C or D affects the chemical potential of A? To understand this point, let's look at the chemical potential interpreted physically. So here is a system made entirely of A-type atoms or A-type molecules. Of course, this system has some internal energy, so all these particles are moving around and there are forces between them. There's a potential energy between this one and between this one and that one. Of course, the further away the particles are, the less is their interaction. Now, imagine that we add one more A-type particle to this, then this A-type particle will interact with all the ones around it, not too far, but a lot of particles around it, and so the internal energy of this system now is going to be different. In fact, the internal energy of the system has gone from an n-particle system to an n+1 particle system, and then if one uses the definition of the chemical potential, then mu is approximately u of n+1 minus u of n divided by the change in the number of particles, which is, in this case, just 1. The better expression to use is dG by dN, which can be interpreted similarly. That is to say, you add one more particle, and so the change in G is this, divided by the change in number of particles, but here the pressure and the temperature have to be held constant. Now, all this was for the case of one extra particle that was added in, but we can add in a different kind of particle, call it B, over here, or here, or here, or here, or here. And so now we have two species which live together in the same volume. Our definition for the chemical potential becomes this, where explicitly the number of B particles is held constant, and equivalently, the chemical potential of the B species of particles is then dG by dNB with Na held constant. As you can see, now we have a much more complicated situation because not only do particles of type B interact with other Bs, but they also interact with A's. When Na is equal to 0, we have a pure B-type species, and when Nb is equal to 0, we have pure A. Let's see if we are able to compute the Gibbs free energy for what is absolutely the most simple system, and that's an ideal gas. Here we will use the relation discussed earlier that dG by dP, that is how the Gibbs free energy changes as a function of pressure at constant temperature and constant number of particles, that derivative is equal to V. Well, this is an equation that is very easily solved. Here the fundamental theorem of calculus says that the integral will have P at the top and it can start anywhere from the bottom. Of course, if P is equal to P naught, then this term goes away and we'll have G at P naught is equal to G at P naught, which of course is a consistency condition. At this point, you might want to refresh your calculus and see that if I do a d by dp on the left side and I do a d by dp of this integral, then of course I get this equation back. Of course, I've introduced a new quantity over here, P naught. Does it matter what P naught is? Well, it's an arbitrary reference point. That means it really doesn't matter. But once you have chosen it, then you better stick to it. Otherwise, you'll get wrong answers. So if I've chosen P naught to be 1 atmosphere, I must keep it equal to 1 atmosphere for the rest of the calculation. To proceed with the calculation, let's use PV is equal to nRT. That means that this integral is nRT integral dP over P, and that's logarithm of P, as we've seen many times over. And when we take it between P and P naught, then of course that is just nRT log of P by P naught. This means that G of P is then equal to this, and if I take the derivative with respect to n, then mu is just dG by dN, which is RT log of P by P naught, and that is the chemical potential of an ideal gas. You note that when P is equal to P naught, this becomes log of 1 and mu becomes 0. Should we be surprised by this? No, because all potentials are with respect to some reference point. Here it is often convenient to choose P0 at the standard temperature and pressure point. That is, temperature is 0 degrees centigrade, pressure is 1 bar. Finally, let's see what happens if we have two ideal gases within the same volume. So initially it is all A-type atoms, in which case the pressure of the atoms A is proportional to the number of atoms of type A times RT over V. If there's a second gas over there, B-type gas, then the pressure for that will be proportional to NB. Remember that these are two ideal gases, one doesn't know about the other, and these atoms are banging against the container, therefore their pressures simply add up. A useful variable is XA, which is Na divided by the total number of atoms, and similarly XB, which is the number of B atoms divided by the total number of atoms. Of course, if I add XA and XB, and now these you could say are partial quantities, they are ratios. The sum of XA and XB is obviously equal to 1, as you can see. And you can also see that PA then is XA times P and PB is XB times P. If we look at the chemical potential of A, then mu A will be RT log of PA over P naught. But PA is simply this, and so we have that. Similarly, mu B is this. Now, if you take as the reference point P naught equal to P, then mu A is simply proportional to the logarithm of XA and mu B to the logarithm of XB. In a real gas, of course, there will be more complications. That's because you will not have P as simply being equal to PA plus PB. One is going to have an interaction with the other, but that happens only when the densities are very high, when the particles are close to each other, and of course that becomes a much more difficult problem.